Good morning, good afternoon. My name's Andrew Edgar from IBM, and my colleague Richard Johnson, also from IBM. We're going to be talking about our adventures with KubeCF. So the contents of today's talk is we're going to talk a little bit about our motivation, moving from BOSH-based to Kube-based Cloud Foundry, and then a bunch about the specifics on how that was done, from zero downtime update through DNS changes to some of the PRs we submitted and talk about draining, etc. So first of all, talking about our migration and motivation. Right now, we have some very large BOSH VM-based Cloud Foundry instances, and we want to move to Kubernetes-based Cloud Foundry for several reasons. One is cost savings. A lot less virtual machines are required in a kube-based environment with more modernized infrastructure. You know, having operational benefits of having the smart IaaS layer instead of just plain VMs. It also is much more standard with a lot of the IBM services that we have now that are all Kubernetes-based, allows for our operators to be able to manage in Kubernetes rather than some in BOSH, some in Kubernetes. So to get started, we want to talk a little bit about we have very large BOSH Cloud Foundry deployments where we want to have a zero downtime migration, which is mostly transparent to our customers. So they don't know that we are migrating from BOSH-based to Kubernetes-based. And we're going to do that in several steps. So I'm going to start just by looking at the diagrams easily. So this is where we start. We have a BOSH control plane, a BOSH deployed of all the control plane components, multiple BOSH cell deployments, one per AZ in each environment, and then we have our databases, which are bare metal for performance. So to migrate from the BOSH side to the Kubernetes side, we will first bring up Kubernetes cells in Kubernetes and hook those to the BOSH control plane so that applications can be deployed in either the cells on BOSH or the cells on Kubernetes, and it's pretty much transparent. We will then shut down the cells on the BOSH side. And as you shut down, it's similar to a rolling deployment where you deploy and updates. When the cells go down, the applications move. The applications now will move over to the Kubernetes side. And now we have all our applications running inside of the Kubernetes cells cluster. Next step is bringing up the control plane in Kubernetes in a different Kubernetes cluster, where the control plane on BOSH and the control plane on Kubernetes can both manage at the same time, connecting to the same databases and deploying to Kubernetes-based cells. Finally, we will remove the BOSH side of the control plane, and now we've migrated over and everything's running in Kubernetes. So how do we do that? Now, there's one key element that we do is using DNS. To be able to resolve the internal addresses running both on BOSH and on Kube, we need to have a DNS solution that resolves the same domain by different DNS servers with different results. We had to develop a new plugin to Core DNS called FanMerge, which will send the DNS requests to multiple servers and combine the results. We also had to do some delegation to delegate some of the DNS requests from a single Quarks DNS to multiple Quarks DNS to resolve the cell IPs. So in a diagram, we have all components pointing to the merge DNS pods inside the KubeCF control plane to resolve addresses like service.cf internal. It will send requests to the BOSH DNS side and the Quarks DNS side and combine them so that we get IPs for both. And then if I need to get the IPs for cells, I will send the request down to the Quarks DNS on the cell cluster to get the IPs for all the cells. So one of the other items we had to do and look at is when we're doing updates. Right now, in BOSH, you can do max in flight, you can do canaries, and it works really well. KubeCF does have the support for canaries, and it does have multiple AZs, but it doesn't quite work the way we need it, especially for a large deployment where you have, hundreds of cells or, in the 10s and 20s and 30s of components in the control plane, where you can't be just doing a single pod at a time when you're updating. And right now in Kubernetes, KubeCF, it uses stateful sets for all instance groups, which only allows you one pod at a time to be updated during a rolling deploy. So the current multi-AZ support in KubeCF does create a second or third stateful set, one per AZ, which does give you a little bit of parallelization as all stateful sets are updated in parallel, but it still gives you the problem where it's the max number of your AZs. So we added a little bit of an improvement where we could add even splintering that even further to create more instance groups for AZ. So I could have 2 or 3 per AZ and then get multiple to be able to update in parallel. This works really well in cells and some other components like Doppler, where you don't really need the canaries or enforce one at a time. There are some components that we can never update in parallel. For example, the BBS. We can never have all 3 BBS instances, one in each AZ, down at the same time, because then we would have issues with the database being unavailable. So we needed to have kind of a hybrid. Some use multiple AZs and some don't. So the ones that don't, we found there's a new feature in Kubernetes to use topology spread constraints in a single stateful set that will deploy across multiple AZs and ensure that one pod appears in each AZ. So this was really useful to ensure that we have a single canary and update one at a time for those components. Now, both of these are important, and we'd love to work exactly like BOSH does, and there is light at the end of the tunnel. There's a new change in Kubernetes coming to allow for max unavailable on a stateful set, which will allow us to update, to have that max in flight on a single stateful set. So instead of being constrained to one pod at a time, you can say, okay, I'm allowed to have 5 unavailable, so that means I can update 5 in parallel. So I do want to talk a little bit about some of the PRs that we submitted. One, in KubeCF side, we decided to separate Locket from the Diego API pod to make sure that we can scale Locket independently and not have a hard dependency between the Diego API, say the BBS node, and the Locket nodes, which is also useful in future in other deployments that use Irene, where Locket is still required, but you don't have the Diego API pod. We also re-enabled the CC deployment updater that was turned off in KubeCF, but it allows for our rollout deployments with the v3 API. Now, some of the solutions that we talked about around DNS4 is we needed to use the service IP or the service DNS name, and we had to do some updates to things like NATS, Logaggregator, Agent, Logaggregator to be able to override BOSH links, and so that we can use the DNS name instead of getting the addresses from BOSH links, because that was pretty hard coded and we couldn't do that across both the hybrid BOSH side and the Kubernetes side. So we wrote some PRs so that in our BOSH deployments and in our Kubernetes side, we override that and use the service name. So I'm going to hand it over to Richard now to talk a little bit about draining.
Thanks, Andrew. Yeah, so Andrew talked a lot about the the real world things we had to do to augment the base KubeCF, and another one in real world that's important to us is draining. So we have in our large public environments on BOSH today that we've had for years, we are frequently doing maintenance at least every month, and often weekly or even more frequently, where we'll roll the entire deployment. All the cells will get updated, all applications need to be drained, and doing that because we need to try to preserve availability of apps. Even single instance apps, we're trying to make sure that they don't have any outage, because we want that drain support that is common across many of the Cloud Foundry jobs on the BOSH to work. And so, for example, we don't want a cell to shut down all of its apps until those apps have been evacuated and stood up somewhere else. So we found that this just really didn't work, and the KubeCF, I think a lot of people were taking advantage of how fast Kubernetes is at spinning up and down things, which, is good, but it still was disruptive the way Drain wasn't working. So we wanted to go better than that. We spent a lot of time working on Drain support. So we found initially there was quite a few problems with this. We found, frankly, the Drain scripts weren't even getting called because there was bugs with the location of the scripts the KubeCF was calling. And then there was more complicated things like, we're dealing with the fact that the whole implementation of lifecycle is different on a Kubernetes platform. So you don't have the lifecycle of a whole VM anymore. You just have individual containers. You don't have monet. You don't have even consistency from job to job, because not all of the jobs on the BOSH side use BPM. And so, we have some of our own custom BOSH releases and so on. And so when those came across the KubeCF side, there was differences in life cycles of the jobs and the way that the Drain scripts run, because some of them rely on BPM, for example. And there was things like, relying on monet, like PID checks and timeouts within those scripts. So there was significant things to overcome here. You could move the slide, Andrew, thanks. So in practical terms, right, it meant there's a few problems, right? First of all, by default, Kubernetes isn't going to allow any time for the pods to do something like a drain. So we had to set up termination grace period to accomplish, basically give the pod the time to be allowed to try to accomplish draining. Then we had to get the drain script locations fixed. And then even when we'd done that, we ran into a much more difficult problem where we realized that the way that draining was working in Kubernetes is that each individual container was independently draining and ending. So let's take a cell, for example. Garden is one container, rep is another container. On the BOSH side, for drain to work for the whole cell, Garden needs to keep running until rep finishes draining. But on KubeCF, what we were seeing is that Garden as an independent container would just shut down as soon as it was finished, and rep would be broken because it lost its Garden sibling container in the pod. So this required another solution. So, we worked a lot with some great assistants from Suzy team, Yann Dubois and Mario Mano, who have been really great and help for us to figure out how to combat some of these things. So improvements were made to the way that BPM is mimicked, so that the life cycle on the Kubernetes side matched some of the BPM stop and start and so on life cycles. And then this problem with container independence was solved by having each individual container in the pod write to a shared file system, and then each one of those containers would actually pause and wait for all of the other containers to have written to that shared file system. So there was a way to link the life cycles together so that they could all see one another, and only when all of the containers had finished all of their draining work would the actual pod termination and full container termination complete. And that gave us the end result we wanted. We had the drain support like we have in BOSH. Another thing that just will quickly touch upon is that we had to do some sophisticated networking stuff here to link all these multiple clusters and BOSH side together. We wanted, because of the federated DNS solution Andrew talked about, we needed to be able to have addressability from pod to pod across clusters. And the way to accomplish that was we built a Calico service mesh. So we're setting up BGP peering from one cluster to another with route reflections on each end. And that's a way that the IP addressability from one cluster can reference pod and service network IPs in another cluster and connect to them directly as if they were all one. So we've effectively built one logical mega cluster, which is good because Cloud Foundry doesn't understand the cluster boundaries. It thinks that all the cells need to be addressable directly, for example, from the control plane. And so this is how we accomplish that. And I'll just finish on this last slide just to quickly show you what that means. On the left here, within a cell, we can look up the DNS name for the control plane using the federated DNS that Andrew talked about. Using the Calico solution I talked about, we can then connect to it, so you see the ping success. And then, of course, on the right, there's actually some real-world demonstration of that, where we're using CF dot to connect to BBS and query for cells. So yeah, that's how we brought together KubeCF and BOSH, multiple cluster world. And we look forward to any questions that you might have at this point. Thank you.
There is a question in the Q&A tab at the top. What was the problem regarding this? When was the problem regarding the cell drain found? During the analysis or whilst on POC? It wasn't until we started using it, so like, early parts of kicking the tires of it, that we realized that the drain wasn't working properly. And it was pretty obvious, because without even seeing the disruption to apps, what was obvious was that the cells drained instantly. And that was the first clue. I'll reply in text as well, just in case Saurabh's not watching the video.